In this video, I would like to introduce some functions we know, like log, sines, and cosines, and bring them into the complex world, and also show them that they're complex analytic. So here we go. Okay, so I like to start by talking about the log, which is the inverse of the exponential function. So let's try to undo what the function e to the z does. So the first thing to note is that what happens when e to the z is equal to 0? Well, that could only happen. So remember, e to the z looks like this. Like so. And this tells you what the argument of e to the z is. And this tells you what the modulus of e to the z is. So the only way for this to be 0 is for the modulus to be 0, e to the x, and this is the real e to the x function. This is never equal to 0 because e to the x is always positive. So it's impossible for complex exponential function to be equal to 0. It is possible to be any other complex number other than 0. So let's try to invert what we would be. So pick any z that's not 0. And we would like to find u and v such that e to the u plus iv is equal to z. So we need two things to be true. We need e to the u to be the modulus of the z, and v to be the argument of the z. Okay, well, if you take this equation and solve for u, we get u is equal to the natural log of the modulus of the z. Okay, so that's the real part of the inverse. And to get the imaginary part, well, we just take the argument of z. So that will be the imaginary part of the function. Let's check that this guy is complex analytic by checking the Cauchy-Riemann equation. Right? So a couple things. When I write natural log of modulus of the z, if I write this in terms of the real part and imaginary part of z, this is the same thing as natural log of the square root of x squared plus y squared. There's a rule for logs where if you have the exponent inside of a natural log, you could pull that to the front of the log. So you could write it this way. Okay, so natural log of modulus of z could be rewritten this way when we write it in terms of the x and y. And this is a little bit easier to take the derivative of than trying to deal with the square root inside of the natural log function. And as far as the argument goes, there's a few different ways to represent this function. So we just have to use trig. Okay, so pick any point z, and x is the horizontal coordinate, and y is the vertical coordinate. And the argument is that angle right there, that it makes with the positive real axis and the line segment that connects origin to z. So one way to do this is use arctan function, the inverse tangent, and the tangent is opposite over adjacent. So arctan of that ratio should give you the angle that we are looking for. This works just fine, except this formula falls apart when the real part happens to be 0. Okay, so this formula only makes sense if x is positive, So another thing you could do is, well, the modulus is square root of x squared plus y squared, and use arc sine. You could use arc sine of y over square root of x squared plus y squared, or you could use arc cosine of x over that, and that function will work as well. But just for simplicity's sake, let me just work on the case where x is greater than 0 and use this as the formula for this complex logarithm function, and prove that it satisfies the Cauchy-Riemann equation. So this is my u, and that's my v. Derivative of u with respect to x. So derivative of natural log is 1 over the inside. And by chain rule, I multiply by the derivative of the inside with respect to x. Derivative is 2x. The 2 and 1/2 in front will cancel out. And we have, that's the derivative. Okay. According to Cauchy-Riemann equations, this should be equal to derivative of v with respect to y. So let's do that. So v is arctan. So the derivative is 1 over 1 plus the inside squared. That's the derivative of arctan. And by chain rule, I have to multiply by the derivative of the inside with respect to y. So 1 over x part is just a constant, and derivative of y is just 1. So I just have 1 over x here. This looks different from above, but actually, if you multiply top and bottom by x, we'll have x over, on the denominator, I have x squared here that I can distribute. And I do get exactly the same expression as before. So that half of the Cauchy-Riemann equation is satisfied. Let's check the other half. So derivative of u now with respect to y. So this is very similar as before. You just have to multiply by the derivative of the inside with respect to y. So this is the expression we get. And if we take the derivative of v with respect to x, then I should get the negative of what we just got before. So let's take the derivative. So 1 over 1 plus the inside squared. And by the chain rule, I want to multiply by the derivative of the inside with respect to x. So derivative of 1 over x is negative 1 over x squared. And then so I have negative y on the top. And if I distribute the x squared, we get what we wanted. So this function does satisfy the Cauchy-Riemann equations. These guys are continuous as long as we stay away from the origin where the denominator is equal to 0. Other than that, it's analytic. As far as the notation goes, I'm going to use log as a shorthand that's going to be the name of the complex logarithm function. I know in some like 100 level math courses, when you encounter something that's written log, it's usually taken to mean base 10. But I think you are in upper division math course now, and it is actually the convention that in higher level mathematics courses, when you write down log, the expectation is that the base is implied to be e. I know ln it's probably the notation you learned first, but log is what gets used in practice. I am sorry, it's inconsistent with what you've learned before. In fact, if you go to computer scientists, they are more likely to use log as base 2. So they do it too. I don't know if that's a justification. I'm just telling you what the convention is. I'm sorry. So that's the convention I will use for this class. And of course, another thing to be careful about is the argument function here is multi-valued as it was before. So there's multiple possible argument that works for the inverse, each which is off by a multiple 2 pi I. Okay. If I want to talk about a particular branch, I'll have to specify which argument I'm talking about. If I want to use the principal argument function, so remember this is an argument function where the angle is between negative pi to positive pi, and positive pi is inclusive. Then I will use the capital L log. So this would be a function. It's a real function where the domain is everything except it is not continuous along the negative real axis, because if you come from the top, the argument is getting closer to pi, but if you come from the bottom, the argument is getting closer to negative pi. So it's not continuous there. And well, here's a note on the domain, right, for log. So it's the same with the argument function. It's not possible for you to make this function continuous everywhere except for the origin. So that is impossible, because if you start somewhere and you wrap around, your argument will increase, and just when you come back to the same location, the argument should increase by 2 pi, but if you start with a particular argument and then you come back to it, you're off by 2 pi I in the imaginary part of the function. So you can make that continuous and continuous all the way through the journey. You have to cut it off somewhere. So if you want to work as a continuous function, you have to kind of cut up the domain. So usually what's done is you work with what's called the slit plane, where you cut off the negative real axis all the way up to and including the origin. And then when you talk about a function, there's no way to wrap around the origin and increase the argument by 2 pi when you continuously change the number around. So you could have a genuine continuous and also differentiable function just fine, as long as you work with complex plane where one slit is cut out from the origin off to infinity. Sometimes people like to keep negative real axis because it's a real number. Other people make the slit across the negative imaginary axis. So you could do that as well. You could even decide to keep both and make the slit across diagonally, or it doesn't even have to be straight, but you need to cut it so that you can make a loop around the origin. That's the gist of it, if you want to make a continuous function out of it. Okay. All right, so enough on logarithmic function. Let's talk about trig functions. So in particular, I'll talk about sine and cosine here. There are 4 other familiar trig functions. and you could create them in the expected way by taking ratios. Okay, but we're going to start by looking at Euler's formula. So it turns out that triangle is not a good place to start when you talk about complex version of trig function, is because it's hard to make sense of imaginary angle, but we can make sense of Euler's formula. Okay, and if you plug in negative angle, we get this e to the negative ei theta is cosine theta because cosine is an even function, and negative I sine theta because sine is an odd function. And once we have these two equations, and then if we add these two together, the imaginary part cancels out nicely. And then so we'll get 2 cosines, but if we divide 2 to the other side of the equation, we can write down cosine theta in such a way. You could do similar thing with sine. You just have to subtract the two equations. So if you subtract the equation and divide by 2i, you get an equation of sine. And the key thing to notice here is that when you look at this equation, let's say for cosine, for example, left-hand side of the equation makes sense to plug in any complex value for theta, because e to the complex number already makes sense. That's the exponential function that we know and love. So why don't we take this as a definition for cosine of a complex number? We just use the exponential function because that's already known to us. And same thing with sine. So this is going to be the new definition of our sine and cosine. This is the complex trig functions. Okay. So some properties. There's actually a lot of properties that I want to cover. Cosine and sine, first of all, are analytic function. In fact, they're entire function because, well, the exponential function is entire function. So I can take derivative of this guy and then write down that cosine is differentiable, complex differentiable. So it's an analytic function. We get that for free. And of course, because we started from an equation that works with real variable theta, cosine and sine agrees with the real valued functions of themselves. So it makes sense to use the same notation, the same name, cosine and sine. Okay. Cosine is an even function, sine is an odd function. We can just directly check that from the definition, plug in negative z into the formula, and it's the same as cosine of z. And you'll get a negative sign with a sign. This is the angle addition formula that you probably have seen in your trig class. The way to prove this, I don't want to do it in this video because it's long. But basically, you want to start with the right-hand side, use the definition. And when I say the definition, I mean this definition. So cosine is e to the iz plus e to the negative iz all over 2. Plug that in here and plug in similar expressions for the 3 other trig functions that's listed. Multiply everything out, collect like terms, and simplify. And once everything is said and done, you should get cosine of z plus w, or at least in the definition form. So left and the right hand side are equal, and then we're done. Okay. And that's also true for sine as well. So this is great because so many of sine and cosine like a trig relation that we have is derived from these two equations. So if these two equations hold in complex sense, then a lot of the identities for trig also holds for complex numbers. Which is great. For example, cosine of z plus 2 pi is equal to cosine of z. You could just plug in 2 pi in for w and get this. And same is true for sine. So cosine and sine is 2 pi periodic. You could get sine squared plus cosine squared is equal to 1. So you could get this a couple different ways. You could use the definition directly, or you could start with cosine of z minus z and use the cosine addition formula above. If you plug in pi over 2 for w and use the sine addition formula, you can connect sine and cosine function together. They are pi over 2 radians apart. So this is a familiar identity. So sine and cosine are just pi over 2 radians shifted. Okay. So let's work out when sine function is equal to 0. Okay, let's do that. So sine function is written this way. If the sine function is equal to 0, that must mean the numerator is equal to each other, so they cancel out to be 0. So that would happen if and only if e to the iz is equal to e to the negative iz. But exponential functions are equal to each other only when the exponent is off by multiples of 2 pi I. So if you write iz minus negative iz, set that equal to 2 pi ki, you could simplify this down to z is equal to pi k for any integer k. So sine function is equal to 0 when the input is multiple of pi. And this is exactly what we know from real function, but it also tells us that there's no other zeros. Sine function is only equal to 0 on the real axis. It doesn't turn into 0 with any kind of other complex inputs. Okay, you could do the exact same thing we did here. Cosine is equal to 0 only when z is equal to pi over 2 plus some multiple of pi. Okay. The derivative for sine and cosine, you could use the definition. It's what you expect. Derivative of sine is cosine, and derivative of cosine is negative sine. Try to work that out yourself using the definition. I don't think it'll be that hard. I don't want this video to be too long, but there's a couple more things I want to mention. One is that, let's see. Just because all the trig function, trig identity that I've shown so far seems to hold, it doesn't mean everything about trig function that you knew before for the real function is true in the complex world. So for example, it's a well-known fact that sine and cosine functions are in absolute value less than or equal to 1. And this is just not true in the complex worlds. In fact, sine of I is equal to, let's see, e to the iz, so I, minus e to the negative iz all over 2I. Okay, so this is e to the negative 1. minus e to the 1 all over 2i. Okay. Let's see. Let's take the opposite value of this. I'm just going to use the reverse triangle inequality. E is about 2 point. Actually, I'm going to write it this way. This is greater than or equal to E minus 1 over E all over 2. This is roughly 2.7. 1 over E is something like, oh, I don't know, 0.3 or something. Okay, let me be just generous and subtract 0.4. All over 2, let's see. 2.3 over 2. Yeah, you get my point. It's greater than 1. Not everything you know about trig translates to complex. So you do need to check that identity or property that you think is holding. Another thing I wanted to mention is about hyperbolic sines and cosines. So these sections get skipped a lot. So it's perfectly fine if you have not seen this definition before, but this is the hyperbolic sine function, and this is the hyperbolic cosine function that if you've taken some pre-calc or calc classes, maybe it's possible that you've seen this earlier. Now these guys kind of make sense. It's related to sine and cosine function in a very simple way. So if I plug in cosine ix, this is exactly the cosh function. And if I plug in sine of ix, that is the hyperbolic sine function, something called sinh function. So the imaginary axis is the hyperbolic sine and cosine function. This isn't as out there as you might imagine. Hyperbolic cosine function is actually everywhere. Anytime you see a dangling rope, you are seeing the graph of hyperbolic cosine in a rescaled way. So that gives you some insight about what sine and cosine function looks like outside of the real axis. We'll talk more about how these functions behave in the future. But I want to end the video here. I'll see you guys later.